By the way, when I say that, I'm legitimately asking because I don't know. Life is a blur these days. We're lucky I'm here. Cool. All right. So the pre-order traversal, it's recursive. And this works really well because this binary tree is like we can have a recursive definition of a binary tree. A binary tree is an empty tree or a node that we refer to as a root with a left and right subtree. And those subtrees may or may not exist, and if they do, they're a root of their subtree that may or may not have, and so on and so on and so on and so on. Okay, so it's recursive. So how do we do a pre-order traversal? Well, if the node exists, access the node, then repeat this process on the left subtree. Then do it on the right subtree, and then you're done. Easy. I know it feels like we're cheating. Print the thing out and then just deal with the left and deal with the right. But that's kind of the magic of recursion, right? Is that like that sense of like we're cheating. But we're not really cheating because we're repeating the same thing again, but over there and then over there. So if we follow this, what are we doing? Let's make sure. Okay. Go to the node, access the data. What are we doing with it? Let's just print out whatever it is. It's label A. Go to the left, access its thing. B, go to the left, access its thing. D, go to the left, nothing's there, return, go to the right, access the thing. H, left, nothing there, right, nothing there, we're done. This is the first time we've actually finished any of the calls to a pre-order traversal. Return, we're done. Return, we're not done. Here, no, E, done, done. Now, the roots, we can go to the right, and so on. Okay? Hopefully you see that pattern. If you don't, ask questions now, please. Now, an in-order traversal is a little different. If the node exists, you do the left subtree before you do this node, then you do the right subtree. So, if we do it here, we go here, and before we like print out A or do whatever we want with the contents of this node, we completely finish dealing with the left subtree. Completely finish the left, done. Nothing exists. D, nothing. H, nothing. Done. And so on and so on and so on and so on. You see? So the order should be D, H, B, E, A, I, F, C, G. Is that right? Is that what I had down there? Perfect. And then here, let's see if I can do, okay, let's do a pre-order because I didn't do it. A, B, D, H, E, C, F, I, G. Yeah? Yeah. And then this one, the post order, is a little peculiar because we do the left, the right, then the thing. Okay? Which, if at any of these you're like, where would that come in handy? You'd be surprised. It comes in handy when you need it. It exists for when you need to do it, right? It'd be like, do everything. Like, imagine I'm like backtracking or something, where it's like, okay, go do everything and then finish, right? Like, think of it like moving backward. There's a good sense, there's a good reason we might want something like this. So what do we do here? Well, we do the whole left, then the whole right, then we do the node. So do the whole left, do the whole left, do the whole left, done, do the whole right, do the whole left, do the whole right, H, D, E, B, I, F, G, C, A. Was that right? Perfect. There we go. Now, if you're thinking to yourself, how will I remember this? And I kid you not, in spite of what I'm about to say, you will be shocked at how many people get this wrong on the test. So listen to me right now. Pre-order. What is a pre-order traversal? First of all, there's not a lot to remember with any of these traversals. Function, name of the function, you know, it's a declaration, it's like signature. If the node exists, the magic is pre, in, post. What is the order of this stuff going on here? Pre, we access the thing, left, right. Why left, right? You know, we like to read left, right. Could we do right, left? I guess, but typically we're doing left, right. Okay? So the left, right order is fine. But the pre, we access the data before, pre any of these. For in order, it's in between the recursive calls. And for post order, it's after. It's post. It's after the recursive calls. If you get this wrong on the test, I'm going to be so mad. Don't get it wrong. To be very clear, pre, in, post. If you somehow screw this up, I don't know what I'm going to do. You're going to ruin my week. I'm going to think to myself, how is this possible? I assume the only way it's possible is if you're playing a joke on me. All right? All right. You laugh, but every year, somehow, I don't know. It makes no sense to me. So any question about these pre, in, or post order traversals? They're recursive. Now, I'm not going to put it on the test so I don't get disappointed, I guess. Maybe that's what will happen. These are recursive ones. I could implement this. Actually, no. I don't want to spoil something. Now, level order traversal. This one, typically we don't do recursively. A level order traversal is a little bit different than the other three. We don't go down each branch. Okay? Instead, we go along the levels. So instead, traverse the breadth of the tree. The breadth being like the width as you go down. The idea is you start at the root, visit the nodes in each level from left to right. With this idea, there is no immediately obvious recursive definition for this traversal. Okay? The other ones were fairly obvious. Start at the root, go to the left, go to the right. Boom. You know, like they were all just variations of that. Level order, there's no immediately obvious recursive definition. You could make one. Remember, anything you do recursively, you can do with a loop. Anything you do with a loop, you can do recursively. It doesn't really matter. But some things are a little bit more natural to do one way or the other. So the level order usually goes, so here's the idea of the level order. You start at the root. The order would be A, B, C, D, E, F, G, H, I. That's how you would do it. Okay? So how do we implement this? First of all, by the way, the pre, in, and post are all slight variations of a general style of a search. And maybe search isn't really the right word, but like strategy for traversing. I realize these are all strategies for traversing, but these all fit in the broad category of a depth first, where you go down and you backtrack, down, backtrack, like your mazes, okay? You used a stack on your mazes, right? We've also seen a stack with recursion, the system stack. In fact, it would be hilariously simple for you all, maybe simple is not the right word, but it would be entirely reasonable for me to have the fourth assignment be like, do the maze again recursively. No stacks allowed, just the system stack. And it turns out the algorithm for doing that is hilariously simple. But it uses recursion, which means it uses like a system stack. But this depth first search, like go down, backtrack, push, pop, push, pop, push, pop. Recursion, it's this depth first. We go down and kind of work our way back up before we carry on going down and whatnot. That would have been like assignment 2. Now assignment 3 has a strategy a little bit more along the lines of a breadth first search, one like this, where you don't like go down and back, like you don't go deep first. You kind of like start here and you kind of like move out away systematically, not going down and back, but you just kind of like go and explore the way. How many of you have played like a video game where like it's like an adventure game, right? And how many times have you been like at a point where like you hit like a fork in the road? You can go down various paths, right? Maybe you can go this way, you can go this way, or you can go this way, right? This is a wall. And you're here and you're left going like, oh no, right? Where do I go, right? And like you know that like 9 times out of 10 in a game like this, this may be a really bad map. Okay, this is a really bad picture. you're walking down this hallway, and you can go this way, or this way, right? Which way do I go? Chances are you know. Like, how many times have you been like, man, like, one of these is like the right path, but you know that like, oh, if I go down this path, I'll get like a really good sword or something, right? And down this path, oh, maybe there's a monster and there's a lot of money, whatever, right? But like, you know that's coming. I know you've been in this situation. Which way do you go? And you're like, man, I don't really want to like if I go down the right path, and then like, you know what's the worst? Is when you go down the right path, and there's like a big final boss, and you can't go back, and you're like, no! What if that was like a key item that would have made it like, right? Like how many, geesh, that's such a pain in the butt.
They always go up.
Pardon? Always, is that the trick? Yeah? So, you can't go right, always up. So, I'm willing to bet we all have our own like coping strategy for this situation. What do? Do you kind of cheese it by saving and then seeing what happens? And then like, oh, if it's the wrong, you just, okay, fine. That's your depth first search, basically, right? Or maybe you go a little bit and you're like, does this seem right? I don't know. Let's go check down this hallway. I don't know. And you go down that hallway. Oh, there's a oh, perfect. That's more of a breadth first search where you kind of like go poke and you're like, I don't know. Those are just different strategies of traversing this environment. This breadth and depth. Yeah?
Or you write an entire essay and send it to him at 1 in the morning.
What? I'm not sure I understand.
Causing problems. That is all you need to know.
Causing problems? I guess I'm on the outside of that joke, but nevertheless.
Well, if it makes you feel any better, I feel like I am.
Oh, okay. Point being, different strategies. Assignment 3, the A star was a variation of a breadth first search. Q's are really handy for breadth first searches. Now, A star has a little bit of intelligence to it in that it wasn't like a pure breadth first search. It had this like breadth strategy where it would like look at the next thing, like the next, but like it had priorities. So it would try to prioritize things that were closer to what it thought the output was, right? So like if we're here, and we do a level order traversal, right? And let's say, let me finish describing this and then I'll kind of point out the variation, right? So a level order traversal here, start at the root, left to right. What's the order? A, B, C, D, E, F, G, H, I. Easy peasy. So what would that look like? Here's the simplest thing we do. The function, define level order traversal. If the root exists, enqueue the root to a queue. Okay? So let me draw a queue. Let's say this is my queue. Okay? Then what? While the queue is not empty, dequeue a node, enqueue, access its thing, so I guess like print it out, whatever. Then, if the left child exists, enqueue it. If the right child exists, enqueue it, repeat. That's it. It might look more complicated than the recursive ones, but it really isn't, right? This had the like auxiliary data structure of a queue needed, but like that sounded good. Well done. This one required a queue where recursion didn't need a stack, but it kind of had one by default, so So what's the idea here? Start at the root, enqueue it. So I'm going to say A. A is here. Okay, cool. Now the loop says, well, the queue is not empty, dequeue. Okay, perfect. I've got A. Does the left child exist? Yeah, enqueue it. B. Does the right child exist? Yeah, E. Enqueue it. We're done. Repeat. Is the queue empty?
Shouldn't that be C, not E? Because it would be the right child.
Correct, because I'm looking at B for some reason. Thank you. Much better. C. So now, great. Is the queue empty? No. Dequeue B. I'm not going to move C up. It's at the head of the queue. Dequeue B. Print it out. Does its left child exist? Yeah. Enqueue it. Let's write the letters out. A. We just dealt with B. Does the right child exist? Yeah, in Q it. Great. We're done. Does the Q, that iteration of the loop, is the Q empty? No. So DQ. Does the left exist? Yeah. F. G. Let's make this bigger. Yeah, expand capacity. Nice. All right. DQ the D. Does the left child exist? No. That's fine. We just don't do anything. Does the right child exist? Yeah. H. DQ. E. Left child doesn't exist. Right child doesn't exist. Okay. Is the Q empty? No. Get the F. Does the left child exist? Yeah. Does the right child exist? No. Whatever. Is it empty? No. G. Left and right child don't exist. Is the Q empty? No. H. Left and right don't exist. Whatever. I. Left and right don't exist. Whatever. Is the Q empty? Yep. We're done. So the magic was in the Q. Now, where was the, so like the point being, like I add A, B, right? I go down to B and I then have to like add D and E, but C will get dealt with before these two are because they are like necessarily added to the Q behind C. There we go. To go back to the point I was making about assignment 3, the variation here would be like, well, when I was adding the elements to the queue, I'll just do a simple example because there's a lot more nuance when it comes to like A star. But let's say I'm adding B and D, right? But let's say like because of A star, my heuristic is telling me that the answer is over here. Or no, let's say that the heuristic is telling me the answer is over here. So although I'm adding like, okay, B gets added, but when I go to add C, because the heuristic is telling me it's closer, it gets added to this queue, but like before B. So I would like prioritize it. Then I DQ it, and then I'm adding G, which should go in front of B again because the heuristic is telling me to. So it's still a queue, but the priority queue is how we like added the intelligence to it. All right, iterative, pre, and post order. So, okay, let me put it this way. What do you think would happen if I changed out a queue for a stack right there? Imagine I put it in a stack. I'll give you a second to think about it. It's not too bad. You might want to like reorder some of the stuff that you do things, but imagine this is a stack, not a queue. Let's just draw it out if it's throwing us off, right? I start with A. And you know what? I'm going to flip the order in which I push things. I know I say like add left and add right. I'm going to actually push the right and then push the left. So I'll do it in a different order, right? So I added A. I pop A. So I get like, okay, A. And then I push C and B. Right? I pop B. But then I add E and D. Right? I pop D. I add H and nothing to the left, so whatever. I pop H. E. I pop H. Nothing left. I pop E. Okay. Right? Nothing left. I pop C. And then I do G, F. This is the stack, by the way, if it wasn't clear. Do you see? What does this look more like? A pre-order. It looks, at least at the very least, and we can kind of tinker with how and when we're pushing things on the stack, but the point is this is more of a depth first search strategy where we go down and back because we're using a stack, which we were implicitly using with recursion before because of the system stack. So the queue and the stack are really kind of the tricks for like, oh, do you want the depth or the breadth, right? Assignment 1, assignment 2, depth, assignment 3, breadth. Cool? Cool. I think it's fun. All right. Now, with the iterative level order traversal, a queue is, oh, this what happens if the stack was used? Well, with recursive, whatever, I just showed it to you. All right, analysis. Now, listen to what I'm saying carefully. Maybe this year we'll get it. We'll maybe get it this year. But listen very carefully to what I'm saying. And I know I'm going to put you on the spot, so you're going to want to try to jump to an answer really quickly. But let's try to take our time and understand. Listen to what I'm saying. Here, n is the number of nodes. Okay? So if we're looking at this, n would be 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 in this particular case. But in general, imagine some arbitrary tree with n nodes. Whoa, don't look. If all n nodes are to be visited, what is the computational complexity of these traversals? Now I'm worried that by emphasizing that n is the number of nodes, it's now making you suspicious, so it's slowing you down, but maybe you would have been fine. If n is the number of nodes, and I need to visit each of these nodes to access it and like print it out, what is the computational complexity of these traversals? Yeah, perfect, obviously. Why? Well, for every node, I gotta put my finger on it, right? And you might say, well, it's recursive. You put your finger on it, you go down, then you come back. Yeah, but when you put your finger back, that was still like the same, right? Either way, it's constant time. Who cares? Now, the reason people get kind of thrown off by this is because if we look at, do I have an example? If you look at this, now that's not Java, but of course this is pseudocode. And you look at this and you say, well, hold on. Let's go back to like pre. It's maybe the like nicest version. You look at this and you go like, well, hold on. I remember with Fibonacci, the weird thing with Fibonacci, the reason Fibonacci was like bad was because for every time this was called, it like spawned 2 more calls. And then binary search, we saw an example where like, well, okay, although there were 2 recursive calls, only 1 could ever run, right? So for every call of the binary search, only 1 more recursive call would happen, right? At most 1. Where here, 2 are going to happen, unless it's empty, right? But it's going to call it on the left and the right, no matter what. Meaning for every call of this, it spawned 2 more, which was what's created that like exponential growth with Fibonacci. So why on earth is this not following that same funny pattern? Yeah.
There's no repetition. Like you don't do the same thing twice.
Well, but that was, so yes, that's connected to the Fibonacci thing. So what made Fibonacci ultimately worse? Like what made that algorithm, the recursive one, worse than the iterative? It was because of the repetition. But the point was the algorithm made 2 calls. So that's definitely related, but not what I'm trying to get at right now. Yeah. Exactly. That's exactly it. Because it's related to the height of the tree. The height of the tree is more what this would be connected to, not the number of nodes. Now, if you remember, though, there was a nice relationship between the height of the tree and the number of nodes in the tree. The relationship between the height and n was kind of like 2 to the n, right? Yeah, close enough. -1, +1, whatever, who cares, right? But there was a relationship between the height and this. So When we're talking about computational complexity, yeah.
Isn't it n equal
Yep,
to h?
I've got it back. That would be the log. No, of n. And then n, it'd be like 2 to the h. That's better, right? Ish, right? There's more nuance to it, but close enough, right? That's what it's going to grow like. So when we're talking about computational complexity with this stuff, what is n? What is h? When I'm saying it grows like, if I were to talk about what this would grow like if I really cared about with the height of a tree like this, that's a different story. But where n is the number of nodes, it's one thing, height, another. It all depends on what are we actually using as like our basis. Cool? I think that's pretty neat. So just be aware. All right, yeah. Okay, so intuitively, all n since the nodes must be there. But the question was changed slightly. Consider a binary tree of height h. What is the computational complexity of this traversal? Well, it would be like 2 to the h. That's where it would differ. It all depends on like what frame of reference are we talking. All right? All right. Now, okay, let's build one. We talked about what a binary tree is. Let's make a binary tree. Okay. So, well, in order to make it, although we don't need an interface, it's probably nice to define it with something like an interface. So let's make an interface for a tree and then like a binary tree or something. So what would a binary tree need to do? Whatever we want it to do. But let's think. Check if an element exists in the tree, right? Here's a tree. Hey, does this exist in the tree? Why not? Count the number of occurrences of an element in a tree, right? That seems like another reasonable thing too, right? Why not? We could do this with another, like a bag or a general purpose list, like how many 5s are in this list? Is there a 5 in this list? Yeah, same thing, but we could do this with a tree. Why not? Let's check if it's empty. Let's check its size. And we might want some like traversals. Which one? Whatever one we want. We learned about a few, right? Add an element? But where? Where do we want to add an element? Adding an element's kind of funny. Like think about the indexed bag. When you added an element, you would often, the way we did it, you either didn't specify where and it would append to the end, or you add an element to, with a specific index. Well, given a tree, can you index a tree? Not easily. I mean, I guess you could if you made it that way, but I mean, intuitively, there's not really a good clean answer. So where do we add it? It's not sorted, so if I don't know, this is weird. Where do we add it? I don't know. Where? If I want to remove an element, which one? From where? How do we do that? These are tricky.
You more need like an address rather than an index.
Yeah, we would need something, that's for sure. So this is kind of a weird one. Maybe it doesn't really matter where we add it. Maybe we should add it in a way where like it grows left to right. That's kind of reasonable, right? Yeah. Like if I've got a tree and you say add an element, okay, put it here. Add another element, put it here. Add another element, okay, put it here. And then here, and then here, and then here, and so on. Well, we could do it that way. But the point is we would need to define our tree to work that way. The general idea of a binary tree, that's not a rule. We could make it a rule for ours, but that's just, this is a binary tree. How we added it, that's not part of what a binary tree is. So we've got some peculiarities. When adding and removing from a stack or a bag, it was a little bit more straightforward because they were part of like the definition of those collections. When you add something to a stack, where it goes was part of the clean, clear definition of a stack. Similarly with a queue. Bags got funny because we had to, well, it was more general purpose. A tree, for example, where do we want to put it? Well, it depends in a similar way that it depended for the bags. So, okay, but what exactly, typo there, but what exactly add and remove means may differ depending on the specific type of binary tree we want. we're going to implement a very specific type of binary tree. But for now, we're just going to define the interface of a binary tree, a general purpose binary tree. Then we will inherit from that to define a specific one in the same way we did with a bag. We defined a bag, and then we defined a sorted bag and an indexed bag. We're going to define a binary tree, and then we're going to define a very special type of binary tree. But let's define the interface, okay? Public interface binary tree extends iterable. We want this collection to be iterable. Add, remove, contains, count. We're defining the fact that it's going to be able to add, remove, but how? I don't know. This is just the interface. Contains, count is empty size, and then we have a bunch of iterators. We've got our general purpose iterator. This one must be implemented if we extend iterable. Okay? So we must have a method called iterator that returns an iterator. But we included 4 more that are returning iterators. These don't need to be there to be iterable, but we can have whichever ones we want. However, like we talked before, what will this one be? It's going to probably be one of these 4. One of these 4 is going to have to be like our default one, but which one that is, it's entirely up to us, whatever one makes sense for our needs. Yeah?
So could you just put the iterator and then one other one?
You could have only one for all we care. It really, all we need technically to be able to be iterable is having one. So we could exclude these, but this one will return an iterator that will either be in a pre-order, in-order, post-over, or level order traversal, presumably, because those are the common ones. We could define whatever order we really want, but you'd be weird if you start to go like non-standard ones. Yeah, you'd throw people off. So chances are, if we crack open our implementation, this one's just going to return the result of calling one of these 4. But yeah, cool. Cool. How are we going to implement this? We could do it with an array. We could. We're not gonna. We're going to do a linked implementation, like we did with like our other linked structures. Except of course, this linked implementation, well, we can't use the nodes we've been using, because the nodes we've been using has a next. We have a left and a right. So we're going to make a new node class, maybe a binary node, whatever, and have it have data left and right instead of data and next. So a variation, but same idea. So no binary tree implementation is going to be created for a basic binary tree. We are going to implement a specific version, a binary search tree, which we will define very shortly. One way to do this is with the linked nodes. Use the size field to keep track of the number of the elements in the tree, and use a field to reference to the root of the tree. And then everything else is kind of done via the head, the root, in a similar-ish way how we did it with bags and other linked structures. But we do need a binary tree node, so here's how we can kind of like visualize it. Here, have the node contain some reference to some data, some element, whatever. A reference to a left child, which would, of course, its type would be another like node like this. And a reference to a right child, similarly, a node like this. A new node, standalone class. A new node, a standalone class, but this may cause confusion between, yes. So remember how like we had like a node class, but then we talked about how we can make it an internal class, right? Because it only really mattered there. Here, if we called the new, we're going to do another internal class here for a binary node. It keeps our namespace nice and clear. Anyway, so private static class, this would be like some internal node, okay? T data, left is a node of type T, right is a node of type T. We've got 2 constructors, one that takes nothing and it just makes an empty node with nothing. And the other one is a node that takes data, that assigns data, and then the left, right set to nothing. People always ask, could you make another constructor where you set the left and the right and so on? You could, yeah, sure, but we don't need to. It'll be fine just like this. Get data, get left, get right, set right. That's it. Yeah?
Is there a reason why everything in this is private?
Yeah, because it's a private static inner class. So it's all accessible. So remember how we did this with like the link structures? The node, this class would exist within like our binary search tree class that we will be implementing in the next topic. So it would exist within it. So everything inside this class has access to it, but nothing from outside that class has access to it. That's just a nice like bookkeeping way. Remember, the idea of the inner classes is like in the same way that you might have like a private method inside a class that's important for the inner workings of that class, but shouldn't be accessed elsewhere. Same idea, but for a whole class. You might say there's a good argument for like, you really didn't need getters and setters. It's a private static class, so why not just manipulate the fields directly? Yeah, okay, sure, fair enough, but let's be good. Use accessors and mutators. Yeah. This is, of course, mutable because we can get data and we can set data. So we could actually go to a node and change its data. A lot of people would feel very negatively about this, but data structures are kind of intrinsically mutable, so it is what it is. You don't need to make data structures mutable, but often people do. Okay, although we are not going to implement a binary tree, we're going to implement a binary search tree, a very specific version of it. We could think about what would the code look like for a binary tree. Now, I could have a tree class have a field called size, right? I could do that. And so if someone wants to know what's the size of my binary tree, I could say, well, return the result of that field. But imagine I was lazy and I didn't write that. Could I calculate the size? Now, if you had a bag or a queue or a stack and you wanted to calculate the size and you didn't have this field, stack's a bad example because you might, but think of like a linked stack. How could you do it? Well, you iterate over the stack and you count 1, 2, 3, 4, 5. Oh, there were 5 things, right? We could do the same thing here. But then we need to traverse this thing. So have a look at this code. First of all, you'll notice that size returns the result of calling size, but a different version, an overloaded version of size. But this is a private one. And you'll notice this one's recursive. So this is an example of like, remember we were talking with the searches where like you have like this like one you call that starts it?
Yeah.
Right? Otherwise I'd call this with like the root or something, or whatever. This is an example of that. Have a look at this code. See if it makes sense to you. All it means is, if the tree is empty, return 0. Otherwise, return 1 itself plus the size of the left subtree and the right subtree. Well, how'd you get the size of the left and right subtree? By calling the method that tells me the size of the left and right subtree. And how'd you calculate those? Recursion, man. There we go. All right. Yeah? Yeah?
Would that be similar to like, although Fibonacci was multiplied?
No, it was still additive. Just think on it. We'll hit it next time because we're out of time.